All right, so for the next example, part C, we're looking at this function is right up here. It's pretty complicated looking, so let's take this down into steps. Y is equal to e to the x squared over x minus 1 over the fifth root of x squared minus 9. Okay, now this is pretty nasty looking, but it's actually probably not quite as bad as it might look. So a couple of things to keep in mind. Up in the numerator, I have an exponential function with a rational function in the exponent. So it's really a composition between a rational function and an exponential function. Exponential functions are defined everywhere. They don't have domain restrictions. But because the exponent itself is not just like an x or something, I do have to look at that rational function independently and decide, does that have any domain restrictions? Well, looking at the denominator here, I can see that one restriction is that x cannot equal 1, because then I would be dividing by 0 in that denominator. So that's definitely not going to be good. That's the only issue in my numerator, though. If I come down here into my denominator, I have the fifth root of x squared minus 9. There's two issues with the thing here. Well, actually, there's really only one. One, I have a radical function. Okay, normally with radical functions, we have to think about domain restrictions, but there is kind of an exception to that rule. If the index of your radical, which is this number right here, if that's an odd number, those types of functions are defined for positive numbers, negative numbers, and 0. It's not like the square root function where we have to have non-negative inputs. Odd indexed radicals, you can plug anything you want into them, even if it's negative. So that won't be an issue here. But the only issue that really does matter is the fact that this entire fifth root is sitting in the denominator of this really big quotient right here. And we still have the issue of possibly dividing by 0. Looking down into my denominator, is it possible to divide by 0? Is there anything I could plug in for x that would make this fifth root of this thing equal to 0, causing me to divide by 0? And the answer is yes, plus or minus 3. I can see that if I were to factor x squared minus 9, I would get x plus 3, x minus 3. Either of these values would cause that to be 0. So this function has almost all real numbers in its domain. There's only 3 numbers that have to be excluded. So I can do what we did before. I can create this number line. Negative 3 is included there, 1 and 3. All 3 of those points are going to be represented by holes because our graph does not include those numbers in its domain. So we're going to go like this. This is similar to our first example up here, where we had almost all real numbers, but just a couple of holes in the graph of that line up there. And what we ended up with was a union of intervals when that happened. So that's going to happen here as well. I'm going to have negative infinity to negative 3, union negative 3 to 1, union 1 to 3, union 3 to infinity. Notice because it's 1, 2, 3, 4 separate pieces, so I'm going to have 4 intervals. That's the set, those intervals together, that's the set for which this function is continuous, because that is also the domain of that function. D. What can I say about D? All right, so kind of coming back up here. D is this function right here, 8 to the 4x minus 6 over log x plus 3. Let me rewrite that down here so you can see it. 8 to the 4x minus 6 over log of x plus 3. So for this function, where are the issues that I can run into? Well, up in my numerator here, I have an exponential function. We know that exponential functions are defined everywhere. However, we had kind of an exponential function in this previous example, and we still had issues with its exponent. We had things that would cause the exponent to be undefined, so I have to look at my exponent as well. But the exponent is a polynomial. It's a linear polynomial, and polynomials are defined everywhere. So we know that there's really no value of x that would ever cause us an issue in this numerator. Also, the fact that this is in the numerator itself means we don't have to think about dividing by 0 anywhere. Down in this denominator, we do have some stuff to consider. So first of all, it is a logarithm, and logarithms we know can only take positive numbers as inputs. So one thing I have to do is make sure that the x plus 3 that's inside there is always positive, always greater than 0. I can solve that easily. I get x is greater than -3. But that's not the only issue that we run into down here. See, the thing is, if this logarithm, if I have a value of x that I can plug in and it gives me 0 from that log, well, that would also mean that I'm dividing by 0 right here. Even though that logarithm would be defined, it's causing me to divide by 0 in the larger quotient that's going on here. So I want to think, what would cause log of x plus 3 to equal 0? We have to say that it cannot equal 0, right? Well, logarithms are equal to 0 whenever the thing inside of them is 1. So that would mean that x plus 3 cannot be equal to 1. And solving for this, x cannot be equal to -2. Okay, now -2 is included in this interval. So when I graph this, I'm going to plot -3 and I'm going to plot -2. This would normally mean that we want to graph everything to the right? But then I'm going to create a second graph for this. This represents all real numbers except for -2. So I have to have a hole there, like that. As before, we saw that what we need is the overlap between these two graphs. So to the left, I can't go any further than -3 because this lower graph doesn't go any further than -3. Both graphs go all the way to the right. So they're both going to infinity, but one of them excludes the number -2. So putting all of this information together, our domain should include the interval from -3 to -2, but it should not have either endpoint because -3 has a hole here, -2 has a hole there. Both graphs consist of all real numbers from -2 to infinity, not including the -2. So really what I want is the union of these two intervals right here. That would be my domain. It would also be the set of all values for which this function is continuous. Okay? All right. So we've now seen several examples in that one theorem that we talked about, which says that all of these different categories of functions are continuous everywhere on their domain. That was really helpful. One thing that does not include, though, is piecewise functions. When it comes to finding continuity or determining where a function is continuous, if that function is defined piecewise, like this one, you can run into more issues than just domain restrictions. So consider this guy right here. This is a piecewise function. F of x is equal to x squared minus 1 whenever x is less than or equal to 2, and it's equal to e to the 0.2x whenever x is greater than 2. Both of these functions by themselves are continuous for every real number, because both of these are functions whose domains are all real numbers. Polynomials, they have all real numbers in their domain, so do exponential functions. However, this piecewise function is not continuous everywhere. And I can see that when I try to graph it. This is what the graph of that piecewise function is. Notice when x is less than 2, I'm looking at this parabola, which comes from x squared minus 1. When I'm looking to the right of x equals 2, I have this little curve, which is part of this exponential function. If we graphed more of it, you would see it doing exponential growth like that. They don't connect. You can see that they're not connected down here. That means we have a discontinuity at 2. Right here is where I could have gotten that hint. 2 is kind of like what I'm going to call a boundary value. It's a number that separates which function we use for our piecewise function. And even if these functions by themselves are continuous everywhere, piecewise functions can cause a break if we have like one of these boundary values like this. So Really what's going on here is if we look at our conditions for continuity, this function is defined at 2. Notice I have a point there. But its limit as x approaches 2 does not exist because the two left-hand sided limits disagree. So what I'm seeing here is the limit as x approaches 2 from the left of f of x is not equal to the limit as x approaches 2 from the right of f of x, which means the limit as x approaches 2, the two-sided limit, does not exist. Okay, this is the main issue that we can run into with piecewise functions, in addition to having functions in here with domain restrictions. We have to now look at both of those things. So you know that we can evaluate one-sided limits in a piecewise function because we've done that before. And so in the examples, we'll kind of investigate that a little bit more. All right, so here's kind of our process for how we find where a piecewise function is continuous. 4 steps. So first, observe which values of x we are given in a rule. So an answer cannot include any values of x for which we do not have a rule. Here's kind of what that means. Up here, I can plug any real number I want into this piecewise function because any number that I plug in will satisfy one or the other of these two conditions. Every real number is either greater than 2 or less than or equal to 2. But I may have defined this differently. I may have said here, whenever x is greater than or equal to 0 and less than or equal to 2, and if I changed this condition and left this one alone, then we wouldn't have been allowed to plug any negative numbers into this function. So that first condition is saying make sure that there aren't numbers that are missing from the rules that we've defined here. Secondly, find any domain restrictions for each of those rules and compare them to the x values that are defined for that rule to see which, if any, are relevant. In my example up here, neither of these two functions by themselves had any domain restrictions, but suppose one of them did. Suppose this function up here was not defined for x equals 1 and x equals 5. Obviously that's not the case, but let's just pretend for a second. Well, that means I could not plug x equals 1 into my function f of x here, because 1 satisfies this rule, which points me towards this function, but I'm saying we're pretending it's not defined at 1. Even though this function is not defined at 5, in my hypothetical here, it wouldn't matter because we don't use this function when x is equal to 5. We would use this one. So that's kind of what it's talking about with that second condition there. Condition 3, or step 3, apply those 3 conditions in the definition of continuity at a point to determine if the function is continuous at each cutoff number. I'm calling it boundary value, but cutoff number is a perfectly good way of describing that. And that's basically saying check for this type of thing happening. See if the fact that you have a piecewise function causes the two pieces to separate. Okay. And then finally, determine a solution that satisfies all of the requirements found above and write your answer using interval notation. Step 4 is where we can write that number line or draw that number line and do that one-dimensional graph. That's kind of what that's talking about. So we have a couple of examples to look at. We want to determine where this function down here is continuous, and we want to write our answer in interval notation as we've been doing, okay? So first of all, if I go through that step-by-step process, the first thing I'm looking for is if there are any values of x in the real numbers which are not met by any of these 3 rules right here. So I'm just looking at the rules. X is less than 0. That accounts for all negative numbers. X is greater than or equal to 0, but less than 10. So that includes 0 and all of the numbers from 0 up to 10. Not including 10. And then this rule here says x is greater than or equal to 10. So that includes all numbers greater than 10, including 10 itself. That covers everything. There are no real numbers that are not satisfied by any of these rules. So we can move past that first step. Okay? Going back to that page, what was our second step? Find any domain restrictions of each rule and compare them to the x values defined to see if they're relevant. So these are the rules, 1, 2, 3, these 3 functions here. I want to investigate each one and see if there's any values of x for which stuff is not defined. Let's start with the natural log of 2x plus 5, okay? So this guy we know, because it's a logarithm, that 2x plus 5 on the inside there has to be greater than 0. That's the condition with logarithms. So 2x plus 5 must be greater than 0, or else that log is not defined. This would imply, after a couple of steps, we can solve for x, that x is greater than negative 5/2. Okay? But look at the rule that actually matters here. So this rule is only used whenever x is negative. So this inequality includes some negative numbers, but we don't need all of it. We need everything that's greater than negative 5/2, but still less than 0. So I'm going to write that this way. Negative 5/2 is less than x, which is less than 0. So this interval right here is taking into consideration the domain restrictions of our natural log function as far as this rule is concerned. Okay, so we're going to leave that there. We'll return to this when we get to our final answer. Looking at our next rule, I have a rational function, 5x cubed over x squared minus 2x minus 15. This is a rational function, and as we've seen, the only time we have a domain issue with rational functions is if the denominator is equal to 0. It does not matter what's happening in the numerator. So we're basically going to ignore that 5x cubed up there, but I am going to pay attention to what's going on down here. So it's going to help to factor that. X squared minus 2x minus 15, that factors to x minus 5, x plus 3. Okay? This only has two values for which I would be dividing by 0, if x is equal to 5 or if x is equal to negative 3. So I'm going to say x cannot equal 5 or negative 3. Okay, that's all I have to do for that one, except before I move on to the next one, I want to see if either of these values are irrelevant. Turns out the negative 3 is irrelevant, because if you come up here, I don't even use this rule unless the value of x that I'm plugging in is something between 0 and 10, not including 10. Negative 3 is not in that interval at all. So if I'm plugging negative 3 into this function, I would never use it in this rule anyways. We can get rid of that one. That doesn't matter. 5 is in that interval, so I do have to pay attention to that. We're going to keep that there. Finally, I have 5x to the power of x cubed minus 12. And this is an exponential function composed with a polynomial. Both of those types of functions are continuous everywhere, so there are no domain restrictions for this last piece of our piecewise function. That means we're done with that second step. Now we're on to the third step, which is checking to see if at any of these cutoff values, if we have differing limits. Okay, so let's think about the limit as x approaches 0. That's the first cutoff number, but we're going to approach from the left first. Okay, so if I'm approaching x from the left, that means x is always going to be less than 0. If I'm approaching 0 from the left, x will always be less than 0, which means I'm only using that logarithm when I'm dealing with this limit. So that means I can just think of this as the limit as x approaches 0 from the left of just this logarithm. And because 0 is in the domain of this function, notice if I were to plug 0 into this, I would get natural log of 5. We know with logarithms that we can use the direct substitution property to evaluate limits. So that means I can actually plug that 0 directly in to the natural log of 2 times 0 plus 5, and this gives me the natural log of 5. Okay? If I plug in, or if I approach 0 but from the right, kind of the same thing. Looking at what we have up here, I have a rational function, and we get to use the direct substitution property on rational functions as long as my denominator doesn't come out to 0 when I plug this in. But if I plug a 0 in here, x squared and 2x, those two terms are going to go to 0, and that negative 15 is all that's left. So I have 5x cubed over x squared minus 2x minus 15. I would get a negative 15 in my denominator, and up in my numerator, I'm going to get a 0. That's equal to 0. Okay, now look at the left and the right-hand limits of our function disagree with each other. These two things are not equal to each other. So what that means is that x cannot equal 0 if we're looking for points where we have continuity. This function is not continuous at 0. If I were to graph this function, there would be a break in the graph right there. Let's do the same thing, but with the other cutoff number, that 10 right there. The limit as x approaches 10 from the left. So that means I'm using values that are less than 10, but approaching 10. And that is this middle rule right here. So I have to plug in, I'm looking at a 10 here. So 5x cubed over x squared minus 2x minus 15. We want to plug a 10 directly into that. I didn't work this out ahead of time, so I have to do this one by hand. First of all, I'm allowed to plug the 10 directly in because it's a rational function, and I'm not going to have a I'm not going to have a 0 in my denominator when I do this. So plugging 10 in directly, 10 cubed is 1,000 times 5, that's 5,000. In my denominator, 10 squared is 100. Minus 2 times 10, that's minus 20, minus 15. So negative 20 minus 15 is negative 35. That's going to be subtracted from 100, so actually that would give me a positive 65. 5,000 over 65. I can definitely simplify that, but I'm not concerned with that quite yet. The limit as x approaches 10 from the right. That's the next thing I want to look at. Okay? So let's think about this one now. The limit as x approaches 10 from the right means I'm using values of x that are greater than 10, which tells me I'm using this exponential rule right here. 5x cubed minus 12. We get to use the direct substitution property here. Okay, so now this one is going to be a massive number. So I'm plugging a 10 in for x. 10 cubed, as we saw, is 1,000 minus 12. That's going to be 500 to the power of 988. Okay, that is a gigantic number. 5 to that power is so large that your calculator is not going to be able to represent that. Clearly much bigger than this. This would be less than 5,000 because I'm dividing 5,000 by a number that's greater than 1. So there's no chance of these two things being equal to each other. And this means that x cannot equal 10, at least as far as x values that make this function continuous. So let's try and put all of this information together. So we have this, 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 and this, all as conditions that we need our intervals to satisfy. Let's take all of the numbers that are appearing in here and put them on our number line. So the smallest one that I see is negative 5/2. Let's do it like this. I see 0 showing up in a couple of places, so 0. I see 5, and I see 10. Okay? Putting all of this stuff together, I can do multiple layered graphs like we've done where everything is overlapping, or if I think it through, I can just do one single graph here. So we're saying that x has to be greater than negative 5/2, but not equal to. So that means I would have a hole at negative 5/2, and my graph will only go to the right from here because it has to be greater than negative 5/2. It also has to be less than 0. However, that's really only as far as this first function is concerned. Remember, this interval came from just the restriction on this first function. It doesn't mean that we can't plug in other values aside from 0. It's just that if we do, we're not using the natural log. But down here, we saw that we're actually not allowed to plug 0 in because we have a break in our graph when we do. So that's going to produce a hole right there. And then the next issue is at 5. We can't plug 5 into our graph so without getting a break in the function. So we're going to have a lack of continuity there. And then same thing, at 10, we show that there's a discontinuity there. But there's no other issues aside from that. So x has to be greater than -5/2, which means we're only going to the right, but we can continue going to the right except for where these holes occur indefinitely. X can get as big as we want it to be past 10, but we can't go less than -5/2, and we can't hit any of these holes. How do we write that as an interval, or in interval notation? Well, it's -5/2, 0, union, 0, 5, union, 5, 10, union, 10, infinity. That accounts for 1, 2, 3, 4, all 4 different pieces. Okay, perfect. One last problem and then we're going to be all done. So we want to determine a value for this number a, which is appearing in a couple of different locations in my function here, for which this piecewise function below will be continuous everywhere. Now right now, if I look at the two pieces of this function, it's got a linear function, which is a type of polynomial, and it's got a quadratic function, which is another type of polynomial. Those functions are defined everywhere. So according to that theorem we talked about, they're also continuous everywhere, at least when we consider them by themselves. In addition to that, when I look at my rules here, this function is defined for all values of x. So whether x is less than or equal to 3 or greater than 3, we have something that we can plug that x into. The question is, at this cutoff, the 3, does our graph have a break in it, or is it connected? And remember, that boils down to the left and right-hand limits as x approaches 3 going to the same value. Well, that really depends on what a is equal to. If a can equal any different constant, then for some values, maybe the graphs will be disconnected, and maybe for other values, it'll be connected. How do we make that distinction, though? Well, what I want to do is find the limit as x approaches 3 from the left of f of x, and the limit as x approaches 3 from the right. This is the same thing as the limit as x approaches 3 from the left of a minus 3x, because again, when we approach 3 from the left, we're using values of 3 that are x that are less than 3, which this rule is accommodating, but not this one. Because this is a polynomial, we can evaluate this limit using direct substitution. I plug a 3 directly in for that x, and we get a minus 3 times 3, which is 9. Notice I don't know what a is, so I can't get any more specific than this. But I can do this. I can approach 3 from the right of f of x, which is the same thing as the limit as x approaches 3 from the right of this quadratic polynomial, because that's the one we use when x is greater than 3. Ax squared plus x plus 4. Again, it's a polynomial. I can evaluate those limits of polynomials with direct substitution. So 3 gets plugged directly in. A times 3 squared, that would be a times 9, which I'm going to write as 9a. Plugging a 3 in for x here, that would be 3, plus that 4, that would be 7, okay? Now remember, in order for this function to be continuous, the only thing that's going to matter at this point is that these two limits, the left and right-hand limits as x approaches 3, are equal to each other. So I need to figure out for what value of a would this expression be equal to this expression. And that's easy enough to find by just setting them equal to each other and then solving for a. A minus 9 equals 9a plus 7. Subtract the a over here to get 8a. Subtract the 7 over here to get negative 16. Dividing by 8 is going to give me a equals negative 2. Okay? And that's it. Now before we close the section out, I want to point something out. So in earlier in the chapter, we talked about the direct substitution property. And the direct substitution property was the thing that said, if you can evaluate the limits of specific types of functions by simply plugging the number in that x is approaching directly into your function. We've used that already in some examples here, and we've been calling that the direct substitution property. Direct substitution applies to more than just those rational functions and exponential functions and the ones that we have specified. It actually applies to any function that is continuous at that point. And that's kind of a big connection to make. So what that comes down to, this is our first page of these notes, is this third condition. Remember, a function f is continuous at a point where x equals c only if these three conditions hold. And the third one was the limit as x approaches c of f of x equals f of c. Literally what this is saying is that if this is true, then to evaluate the limit as x approaches c of our function, we simply take c and plug it directly in to our function. We didn't state this at the beginning of the lecture, but I am saying it now. This is the direct substitution property, just using that limit notation. And that's one of the major things that we like about continuous functions. If you know that a function is continuous at some number x equals c, then you can evaluate the limit as x approaches c of that function by plugging c directly into it using direct substitution. Okay, that's going to wrap up 1.4, and it's also going to be the end of chapter 1 for us.